Tiger Beetle sessions. Tuesday, 25th of January, session 10. Hey, Yoran, what's up?
Hey Isaac, great to be back again. So yesterday we worked on the segmented array, starting to get into the right path. We first just took a quick refresher of the code. Things looked good, added a few assertions. Then we started, that's the whole read path done for the manifest of the LSM tree. Now we're looking at the actual write path. So as we're compacting tables, how do we go and update our in-memory metadata? And we're thinking of like a batch update strategy where we go and mutate and insert, remove stuff, and then afterwards we just rebuild the indexes one off quickly. And we ended off with, yeah, some nice to-dos where we can pick up today. So we've got insertions working into the segmented array, and we're thinking to do removes with a little bit of fixer-uppers to combine nodes that are not too empty. And then we can do some unit tests and then see what we're excited about. Yeah. I don't know, does that cover
Cool.
everything?
I think that covers it. We've also left a little to-do note here, which covers those things, then see. Yep. So, shall we just get right off the bat with the moves then?
Yeah.
Or do you want to take a look back at insertions?
Um,
Yeah.
yeah, let's maybe look at it again and we give it another once over.
All right. So here's our entry point. We have a batch API in case we need that and want to optimize it later, I guess. And we also just have a normal insert element API. Um, we handle an empty segmented array especially here. If there's no nodes, then we create an empty node. Um, and otherwise, we check if the node's full before we do any insertion and split it if it is full to make space, returning the cursor to insert at.
Yeah.
And we can assert that there's capacity in the node.
Okay. Nice.
Yeah. This actually isn't maximally efficient. We end up doing more copying than we need to here. Um, this is not, I'm not saying we should do this right now, but it's a future optimization we could do. Because split node does one copy, but if it knew about the element we're inserting, if we knew where that was, we could avoid doing the second copy here. Um, you see what I mean? Like if we left space in the right place while we're copying between the two nodes, we could potentially avoid the second copy, but that only works if the element's being inserted into the second of the two nodes. Like if it's in the second half of the node being split.
Of
That's may not
course.
be worth it.
Yeah, yeah.
Um, I just
Uh,
saw that just now though.
yeah.
My intuition is just to not pursue that yet,
No.
and just get the code running in the most simple way possible.
Yeah.
Because the interface seems fine. It's
Mm,
the only interface that really makes sense here,
yeah.
and so optimizations can come in the future
Yeah. Also to
without breaking
implement
anything.
exactly. And I think to implement that we would have to change this internal interface like split node if full.
Oh yeah,
We,
we have to refactor things a good bit, and it would be
mm,
messier
yeah.
and more complex.
Yeah. Cool. No, we'll give it a shot in another time. And the
Cool.
yeah, we can just keep going, keep closing the loop. Oh, by the
Sounds
way,
good.
just to talk about the near future, like once we get our LSM tree up, then we'll be doing queries, like doing relational
Right.
queries over our nice indexes that we've got. And it turns out that the algorithm, if you've got, say, like you've got two indexes, so I've just mentioned it to you so we can start to think about it already, like for a month or 2 months down the line. So if you want to do a query and in Tiger Beetle and you say, right, get me all transfers where the transfer amount is less than $1 and where the transfer is debiting this account. Now
Okay.
we've got those two indexes, but to satisfy the query, we have to do an intersection, like a set intersection. So the one way you can do it is actually just iterate through both indexes, getting the primary keys out of them, and then in memory do a big intersection of all the primary keys, which could be
Right.
huge. Like, I mean, both these indexes could be from the beginning of time. They could both be really massive indexes. So doing that doesn't really work. You could stream it, but it's still, especially you could have these two indexes which are massive and they only overlap in a very small area. So it's going to take you a long time to actually get the overlap. No, normally, like if you've got
Yep.
two indexes to intersect and one is small, then it's not a problem because your intersection is bounded by the size of the smallest index. But if both indexes are huge, then it's a problem. Like, what do we do? So it turns out, it, yeah, there's a very cool algorithm called the zig-zag merge join. Yeah.
Neat.
And the reason why I bring it up now also is because it actually will use our manifest. So the way to do it is not to stream all the primary keys out of both indexes and then intersect them. The way to do it is actually to start with both indexes, start with a table info iterator for each. And then you operate at the index level, being where the index level in this case is the table infos, and you see, do they have some possible overlapping range? If not, then you
Yeah.
advance the one cursor, compare it again, and then maybe you advance the next one. So you zig and you zag. That's how the algorithm works.
That makes sense. Yeah. I was assuming it'd be something like that.
Yeah, yeah,
Um, we should be using these same iterators with a different callback,
exactly.
or a different, yeah.
Yeah. And but actually really like leveraging the manifest so that we don't have to hit disk. And then the trick is we just want to be able to generalize that so that it's actually you can do like a k-way zigzag merge join. So
Yeah.
we wouldn't need a min heap there because we only check for equality, but something that we can zigzag across a whole. Yeah.
Cool.
So just to keep, yeah, I've been thinking about this problem for a while, and now finally I just hit the right Google query and came up, it's called zigzag. So yeah,
It's pretty funny.
yeah,
Nice.
yeah.
All right. Are you good with the insertions? We try removal now.
Yep.
Um,
I don't know if it's just the graphics buffer, but there seems to be two backticks. Yeah, on line 7, if you go upstairs, line 7.
um, like this
It's,
line.
yeah, it was just the graphics buffer. It's gone now.
Yeah. Cool.
Yeah,
Yep. Just compression errors, I guess.
yeah,
Discords encoding. Or artifacts, I mean, errors.
yeah,
Anyhow, let's try remove.
yeah,
So remove, I guess, takes an absolute index and removes it.
yeah.
Is that's all right? I guess I could, yeah, remove element.
I think it might.
We need to take an absolute index.
It might be that we want to do multiple as well, so that we can. It
Okay.
doesn't. It doesn't have to be, but
How do we?
we.
What would be the API for multiple? Is that like a slice of absolute indexes, or
Yeah.
is that
Because
a range of indexes?
the tables that we selected compaction that we remove are contiguous, like they.
Okay.
So it would be a slice of indexes then.
Well, wouldn't it be just a range of indexes, like a min index and max index to remove? Like we wouldn't need to pass
Um,
in a slice with every index if they're all contiguous indexes.
yeah. No.
Um,
Of course. Yeah. Okay. Yeah. That's even better.
so let's try that then. So we've got remove element now.
Hmm.
Er, and then remove elements.
It actually might be
Uh,
better to pass in an index and a count.
okay, yeah, that makes sense. I think it's a better API too.
Maybe
It seems more.
we won't need this, but it seems to mirror, how we do insert elements so that later on we can
Yeah, I think.
optimize.
Yeah, we'll just come back to this one once we've got the remove single element thing down, I suppose.
Yeah.
Yeah. So what's our algorithm here? We need to just first do the same thing and find the location. Cursor for absolute index is what it's called. We probably need to pass in the node pool as well, because we
Yeah.
want to
Release.
get rid of nodes, and that means we need to give them back to the node pool, I assume.
Yep.
We
Definitely.
have a free function there.
Yeah.
Um, yeah, so this will take a node pool. Then you should probably just do get wrapped. All right. Now we can get our cursor. Well, I don't know why it's going to give me that. Anyhow.
Do
Okay, we've got our
we?
cursor. Now we can just remove it, right? So let's, do
Yeah.
you want to do it like without the splitting first, and then that's pretty simple. And then we
Yeah.
can come back. Then we can just like rewrite it right away to split if
Yeah.
we see this
I think
that.
we need to
Uh,
call array.cursor for absolute index.
oh
We
yes,
That might have been why ZLS was doing that. Oh,
that is probably it. Yeah. Um, I'm gonna copy this stuff because I think it's like pretty much the same. It's gonna be
yeah.
like the copy is gonna be very similar.
Yeah.
It's gonna be the reverse of all this stuff essentially.
Yeah.
Um,
And we can assert that the node count is not 0.
yeah. Um, okay. And then so this copy is now going to be copying backwards, right? Um,
Yeah. Yep, it's going to copy backwards.
have we gotten this wrong for the other ones? It seems like it's gonna. Which direction does copy go again? We got
It,
copy.
it,
Dest.length must be greater than or equal to source. That's fine. Yeah, cool.
yeah.
That is right. And then now we do copy backwards.
Oh, if the slices overlap,
Yeah, yeah. That's
destination
right. I
dot.
thought we did got it backwards. This is copy backwards actually above. It makes sense. These ones too.
Is it? Are they all just copy backwards?
Yeah, they are. Because they all have dest is source plus one. And so that means that this pointer is greater than or equal to source pointer.
Ah, okay. And oh, it's using a reverse loop, right? Okay.
Yes.
And why would
So
why
if we did it
does
this way,
yeah. Hmm.
you see, well, the first thing we would do would be to copy node to node plus one. Then we'd copy node plus one to
Of
node plus
course.
two, but then that would be the same thing.
Yeah,
We just fill the
yeah.
whole array with node, essentially.
Oh, of course.
Um,
It's amazing how
I'm
like
surprised we didn't see that yesterday.
yeah, I thought it was correct. Like because I was thinking through it and it's just it
Yeah,
always
it felt
trips.
forward for some reason.
Yeah,
Um,
it really did.
there's one more up here. Split node to full. No, here.
Can we do it?
Okay.
Can we just grab the source quickly for mem.copy just to check we hit them all?
Copy first now. We only have this one mem copy call left here.
Okay, cool.
which is now correct because it's going to go the other way around.
Yeah.
And this is actually, yeah, I'm pretty sure this is fine. Well, how do you do this? It's going to be -1, I guess. Is that what that is? Yeah. I think that's right.
Yeah, so when we do absolute index, that's going to return the index of the element we're removing. Then when we copy from the source to the target, we're going to ignore the current element, and we're going to copy up to how much stuff there is. So it'll be how much stuff there is -1. That'll be the length of what
Yep.
we're copying. And then we'll move it all.
Yeah, we're just going to overwrite the
Yeah,
index, or the element at this index with the next element.
yeah,
And overwrite the one after that, the element after that,
yeah.
and so on, up, and then make the array one shorter by that, or
Okay,
through that.
cool.
Um,
Maybe, Isaac, what do you think we should do here? Like, just take slices to both of these, call them source and target, and assert that they're exactly the same length, and then we copy. Because we don't have a copy
um,
exact.
we could. We also make it more obvious if we did the count adjustment first, and then so we have the same pattern we had before with the +1, except in reverse. We just need to do this count -=1 first.
Okay.
Do you like that more? Seems like it's harder to get wrong.
Yeah,
Um,
that looks better. And it's symmetrical.
yeah. And then this thing can come 4 as well, I suppose. I'll just do it in reverse order.
Hmm.
Um, it doesn't really matter here though. Um, it's now taking cursor node +1 again. Yep. And then just doing -=1 instead of +=1. All right. That seems to already implement remove properly.
Yeah. Yeah, so because we've deleted from this node, subsequent nodes, their index decreases. So that looks correct.
Yep.
And we're going to use node count after we've already adjusted it. So
Yeah, we can also like switch this around perhaps to put this one down here
closer
and just move
to,
pointer up outside of the actual work area.
yeah. We could put pointer like next to cursor and then away from the for
Sure.
loop. Yeah. Yeah, cool. And counts absolute index. That's right. We'll have checked arithmetic on the array count. So we're already checking that the array does have something in it.
Yep. And we also have this, but yeah,
Yeah.
we are, yeah, we are asserting that this is greater than 0 here, and we're asserting that these are greater than 0, and that this is not empty, and the
Yeah.
pointer slice is not empty.
Okay. Nice.
Well, even
So,
if we do go down to 0, if this happened to be 1, we would subtract 1 here and get a 0 count.
yeah.
Then what would happen when we should go look at relative index, which would also have to be 0 then.
Yeah.
And we have a slice from 1 to 1, which would be a 0-sized slice, so we wouldn't do anything.
Yeah. Nice. And the cursor already kind of checks that our relative index is correct.
Indeed, yeah. The cursor
Yeah,
does all the bounds checking there.
yeah,
Got some good asserts.
yeah,
Yeah. Cool. So
yeah,
that's it for move element, really.
yeah.
I'll just I can do this loop real quick. I mean, then we can optimize it a bit if we want. I guess we want to do like while var.
I thought we can just keep using the same absolute index and then just do a countdown.
Oh, we can do that. That works well. Cool. Yeah. Well, var I equals 0. I guess we can do u32 equals 0. Or
While
while I.
less than
It
count.
doesn't really matter which way we count.
Yeah,
Less than count. This is the simplest way to this is like the most obvious way to write it, I think, to make it not have it off by one error.
at the
Um,
end. Yeah, exactly.
at least to
Yeah,
me.
yeah.
Um,
It's actually amazing that most C reverse while loops are always overflowing the integer at the end.
yeah, it's kind of crazy.
Yeah.
Um, one thing we could think about though is that this is potentially less optimal. I think if you remove it backwards, is it better then? Because you do less copies? It kind of depends on where it's at in the node, so it's possible to know that actually.
Yeah.
Um,
Say like
but
the node is full and we're going to remove all the elements from the node exactly. If we remove from the end, then we're going to do less copies.
yeah, so we should just do this backwards, I think.
Yeah.
Um, I think it's always better to do it backwards, no matter where you end up in the node. You always do less copies.
Yeah.
If you're removing successive elements. Cool. So we're starting at absolute index plus count then. We might want to write this differently then. So we could do absolute index plus count minus I. That would be correct. I think it's not a very nice way to write it though.
Yeah.
Absolute
We
count minus I. This is correct, I'm pretty sure.
hmm.
But it's a weird way to write it. I'd rather have it count down, I think.
I think it might be wrong actually, because if let's say absolute index is just 0 and then count is 1, so we're going to have
Yeah, we
0,
got off by one, don't
yeah, 0
we? Yeah.
plus 1 minus 0. Yeah. We can,
Yeah.
maybe we should just do a reverse while loop where
Yeah, I
we,
think so too.
instead of using a continue expression, we do it at the top of the while. Like I've done it like that a bit
Yeah.
in replica.
I think what we want to do is just yeah, do absolute or just current. I don't know what to call it.
Uh,
I. Let's call it I, yes. And then this
yeah,
is gonna be
it's
absolute
cool.
index plus count to start. And then we do our I plus minus equals 1 right here, is what you were saying.
Okay. Sorry, Isaac, I've just got a call. Just a second. I'll be
All
right
right,
back. Okay.
cool. All right, cool. Absolute index. That's gonna be I. So if we start at, say the absolute index is 5, and the count is also 5. So then we're going to start at I equals 10. In that case, we would want to remove indexes 5, 6, 7, 8, and 9. Then we would start at I equals 10. We would subtract 1 from 10 to give us 9. We would remove 9. then we go through the same loop again. This condition's wrong now, isn't it? We want to check if I is greater than 0. Okay, so 9 is greater than 0, so we subtract 1 again, we get 8, remove it. 7, remove it. 6, remove it. 5, remove it. No, it's not
I'm
0,
back.
it's absolute index. Alright, I
Cool.
think I've got it now.
Okay. Nice. Uh,
Though, maybe it'd be nicer to, instead of doing absolute index addition twice, we do it just in one place and just do like I plus absolute index here.
yeah, that's what I was thinking, and rather let I just be a counter. Yeah,
Yeah,
that's nicer.
I think that's good.
Yeah. And then what I do is well, maybe what we should do here is after the decrement, just add a new line so that we show we've grouped the
Sure.
reverse stuff. Yeah. Absolute index plus I. Yeah, that's nice. Are you happy, Isaac?
Yep. I also like kind of stepped through some stuff and it seemed to be right.
Yeah.
Um,
Yeah, if
so that
absolute
seems good to
index
me.
is 0, count is 1, then the loop will run. We will set count to um, we'll set count to 0, and then we're going to be absolute index is 0 plus 0, and that's what we remove.
Yep.
Yeah, yeah. It's quite tricky. Like you've got to be careful that that decrement happens up top.
Oh yeah.
Uh,
These simple loops will get you.
yeah, yeah. Okay, cool.
All right. So we've got that done now, I think. Um, we've also got remove element implemented, but we were
Yeah,
discussing some kind of optimization yesterday where we would then, if we see that we've reduced a node below half full, we would try and merge it with one of the neighbors.
yeah,
You want to do that now?
yeah. That'll be
Is
cool.
that even worth it? Is my question. I think it is. I think
Uh,
we have to do that actually.
yeah,
Um,
we have
yeah.
to for it to be correct. Otherwise, we'll run out of static allocation. We will
Yeah.
violate the nodes are always at least half full property.
What if the neighbors are more than half full though? Is that possible?
It is possible.
Hmm. So what do we do then? We can't.
So I think we just want some kind of greedy algorithm. So we look to our neighbor A on the left and our neighbor C on the right, and then we check. Maybe we want to bias ourselves for the node that's most full. So
What do you mean
what
by
do I mean?
that?
Okay, so I guess so. What we're trying to do is we've now removed an element from the node. Now we want to see, is the node small enough that we could merge it with a neighboring node? Now let's say both of the neighboring nodes have got space now for this node. Then what we want to do is decide which of the neighbors do we prefer. Uh, so the one neighbor, say they both have the same amount of elements, then it doesn't matter. But if the one is half full, it's about to be able to merge with another node. Then we actually don't want to put this node into that one. We would rather put this node into the neighbor that's more full if it has space. Because that way what will happen is we will fill up nodes, and the nodes that are about to become half full are more likely to be removed themselves and merged. I don't know if
Hmm.
I make if that makes sense.
Yeah, I'm not. Not seeing like, but how do we handle the case where there's not enough space in either of the two nodes, or um, can't we hit a situation where both nodes are
Yeah.
nearly full, or both our neighbors are nearly full? Like, what do we do then? Um,
What we can do is we can rebalance. We can steal some. It if you want, like we can go and look it up online. There's some articles about the unrolled linked list where they actually show you all the different kinds
sure.
of merges. There's quite a lot. I don't know. I think Wikipedia doesn't do too much. Uh,
See what Wikipedia does first, then we can move on from that.
yeah.
I guess it just really tells us, yeah, it doesn't really tell us very much. Um, oh, that's a different way to do it.
Yeah.
If this reduces the node less than half full, then we move elements from the next node to fill it back up above half. If this leaves the next node half full, then we move its from all its remaining elements to the current node and
Mm,
bypass and delete it. That makes sense. Cool.
mm. But before
You
we
see how that
run with
works?
that, yeah, that's cool too. Uh, we should maybe
That
copy
seems
that
really
as a,
simple.
yeah, we should write that as a comment. But we should just check. There's might be one more, Isaac, where I've seen one where they give you actually even more options,
Cool.
and you can
I'm
even
sure there's
tune it that,
more ways to do it too. This one just seems like a nice, simple way to do it.
yeah,
Um,
you
you know,
can,
remember
because you
that
can,
what that would be called?
it's like geek something,
Geeks for Geeks?
yeah, let's try that one out.
Hmm. Why is it
A
thinking
little
I'm in
bit,
the Netherlands? Oh, I am in the Netherlands with my VPN. Um,
cool.
how to search what's better on all the lists. Um, insertion. Do we have like a removal thing? Oh man, it wants me to sign up for things.
Oh man.
Hmm.
Okay, I'll try search a little. Uh, do you see? Let me try find it.
This doesn't seem to be having it.
No, it was one where it actually had quite a lot of um, nice examples.
Brilliant.org.
That could be it. There we go.
Delete. Find element in node E. That's the same thing what Wikipedia says.
Yeah. Okay. This was that article.
This the one you're thinking of?
Yeah, I'm pretty sure it was. It's quite a
Yeah, I think
nice.
that's just kind of the normal way to do it. I think we should just do this. It's the simplest by far that I can think of. Because we do
Yeah,
need to wait something that spirals out over the list if we to handle this case. We
yeah,
can't handle, yeah.
yeah,
In the worst case, in the average
yeah,
case, it'll still be like constant essentially with
yeah.
respect to the nodes. Um,
But we don't.
well,
We actually only do the one neighbor node. We don't keep going
we
over
have to
more neighbors.
we usually will only do the one neighbor node, but oh yeah, it actually yeah, then we don't.
It,
Yeah, right. I just read that wrong. I remembered it wrong. You're
yeah.
right. If yep,
So
we only move
maybe
first. We only move enough melons to make it above slightly above half. It'll
yeah,
still be inefficient for bulk removes if we do it the way we're doing it right now, because we're gonna do the same copy like many
Yeah.
times.
Yeah. So we could actually do
I think
that afterwards.
that's true. After we've removed all the elements, though, I think we want to actually just do it like this for now in our single remove function, and then because the bulk insert is also not very optimal right now. It also does a bunch of unnecessary copies. Um, it's just as bad as the bulk remove would be, actually. I think we just need to come back and write bulk functions that are more
Yeah.
efficient.
Okay.
I think that's what it is, and that might be easier once we've got tests.
Okay.
Um, It'll definitely be easier once we have tests, in fact.
Definitely.
And
Yeah.
so, just say from Wikipedia, or we can just like we can delete that or reword it once we were done. So find the node it is in and delete it from the elements array, decrementing num elements. It reduces the node to less than half full. So we've done all that part already. Then we need to have a check to say if node dot counts node is less than
Half.
node capacity by 2. Then we move elements from the next node to fill it back up above half.
Yeah.
Um,
We actually only need to we don't have to be above half, I think. Uh, we only have to just get back to half. It says here to fill it back up above half.
yeah, I think you're right. We just need to get back to half. We just need to,
Yeah.
that makes
What we
sense.
do
Okay, so
we do have a choice here. We can use either of our neighbors.
yes, but I think it makes sense to take from the next one, perhaps. Well, our goal here is to reduce the amount of copying.
Yeah.
Um, and it's simpler to do that if we take from the next one, I think.
Yeah.
Because then we append to the end of our node, and we don't have to append to the beginning of our node. We still
Exactly,
need to
to
keep the
shift
sort
stuff.
order, right?
Yeah.
So
Yeah.
that's probably why people do it this way usually. Um,
Although the more compact our nodes are, you see that there's two goals we must choose between them. The one goal is to reduce copies when we are mutating the manifest, which is good. The other goal is to speed up the read path when we aren't mutating the manifest. So when we're doing like
right.
queries and range queries and stuff, the more compact our segmented array, the better performance we'll get as we query it. So that we actually want our nodes to be more full because that affects the common case. Whereas if we speed up our inserts here, we're only speeding up, like something that happens a small amount of the time when we do compaction. But our goal is to rather we don't really worry actually about the insert time here. We worry more about the querying performance. So we want nice full nodes so that there's less.
Okay.
Yeah.
I'm not sure having the nodes full actually makes querying faster. I think having more nodes actually may help querying more. Then you've got like you kind of you can skip searching through more stuff at the higher levels of the indexing because you've got more nodes.
Yeah.
Um, I think what having nodes full helps iteration speed
Ex-
primarily.
Yeah.
Um,
Yeah. Which will help for queries as we skip
right.
over
Okay. That makes
table
sense.
infos. Yeah.
And so it's the initial lookup, which yeah.
Yeah.
Does it really make that
So
much
maybe
difference though? Use low
I think
level.
it would make like up to half a difference because it's just less cache misses because you're in a the nodes are all contiguously allocated, so they're like an effective cache line. So the denser they are, the better because we're using what we've already we work better with the prefetcher. Whereas if we jump to another node, that's
Yeah.
in a totally different location.
Right. Right.
So maybe let's not worry too much about the copy and then rather optimize for filling up our nodes.
Okay. And say you want to like check both, and then do the one that makes it more full.
Yeah,
Um.
yes. So we can have like a steal left, steal right, and we just decide who we steal from.
uh, okay. Well, I guess think we should just check if either the only case in which we can delete a node is when either the left node or the right node is exactly half full. Um, essentially with the single element removal.
Yeah,
If we remove more elements than once in a batch, then what we require to delete a node is to see if the node being removed from and the other node minus the removed elements is less than the full node in the elements.
yeah,
But with a single element, you really just all you have to do is check if a neighbor in one direction is less than half full, or is already half full exactly, um,
yeah. Because
or half
if
full plus one,
one,
I guess.
yeah, okay. So maybe you think it's not worth it.
Yeah, I think it's not really worth it. I think much bigger optimization is doing batch removal and batch
Yeah,
insertion. Um, 'Cause that'll also allow us. That'll just be so much faster than this, and it'll give us
yeah.
more compaction. Um,
Maybe
that's
we
also
should
where it's
just,
more important to actually do that thing.
yeah. Maybe we should just do it right away. Do removes as batch. Um,
I was thinking I wanted to get tests done for that first, because then you can like
okay,
use the test using the simple version, and then just replace this implementation and have the same function, or have it tested
okay,
against this thing in a loop essentially.
okay.
Um, does that sound good? We can just like copy
Yeah,
this part to the test code and then have it test against the remove elements. We can test this thing against this thing,
yeah,
essentially.
yeah, yeah. Okay, cool. As like independent implementation. Yeah.
Yeah, pretty much.
Yeah, so basically we'll keep remove element, flesh it out,
Yeah.
and then yeah, although the other way to do it is if we want to test it, it's not we don't even actually need this. We could come up with a much simpler reference implementation if we just have an array. That would be better for testing and pretty simple.
Perhaps we can probably do that too. I think this,
Yeah.
I don't know. I think this is still worth having, the remove element function. I think it's also not very complex to implement, so I think we should just do it. I mean,
Okay.
this
Okay.
logic's not too hard.
Okay, let's do it. But then, are you happy after this? Then I think we do tests, and maybe we should just do these batch functions and use them direct
Yeah, I think we should.
because
Um, I think
we're
it'll
on.
be easier to do them once we've got test those. So then we
Yeah,
can like actually try our code instead of just thinking about it.
yeah,
Um,
yeah. No, I mean we can do the tests, but I think writing the test is not going to actually be that difficult because coming up with a reference, we just use an array that we do mem copies on, and you just compare for equality and fuzz it so that and use.
okay.
So we don't, this is maybe valuable if we want like an individual one, but what I'm thinking is if we if we change the way we think of batch stuff and actually have a rebuild phase. So we have like a remove element that removes an element from a node and then doesn't even worry if the node is empty. Uh, and then we can get better
Yeah,
and
yeah.
better, but then we can have a separate call that like called compact, and compact will actually go and optimize the segmented array like and squish everything together as much as possible so that
That's
when we
probably what we end up
finished,
doing. Yeah.
yeah, And
But
that's
it's the
pretty
same logic of this,
simple.
essentially.
Yeah,
We're gonna write
yeah,
exactly the same code. We're just gonna extract whatever we write right now into a function. I think we still have to write this code no matter what
yeah.
function
Well,
it's called in.
compact will give a different result because it'll be able to do more optimal compaction because it'll treat the segmented. It'll actually iterate over the whole segmented array and compact everything.
Oh, that's what you're thinking.
Yeah, so it's something totally different. Like um,
Hmm.
because that'll actually it's pretty simple to do that. It's like brute force. And also for the read path, it's going to be optimal because everything is like as compact as possible.
Okay. That's then like O n and the number of elements we've got stored in our manifest though, which is kind of scary.
Yeah, it's not that bad. If we're thinking of having max 2 million tables across the forest, 2 million times 64, um, that is a mem copy. Even if we mem copy all of it, it's with a millisecond or two. But the performance gain it's going to give on the read path is worth it. Uh, I think it's really, really nice. But and I mean that's in the worst case, whereas it's going to be 2 million over, four big trees. So it's not going to be. I really think it'll give us just nice performance. It couldn't be more optimal,
Okay.
Yeah. And it's pretty simple. It's
Um,
not as complicated as doing like a batch remove elements, which has to compact at the same time. We cut ourselves some slack.
sure, yeah. That
Yeah,
seems pretty simple. Um,
yeah,
I think the easiest way to do that is like with an extra node essentially. Just like take one node and you copy, well, you acting like your scratch node, I guess. You should like copy from the first thing into that, and then from the second thing into that, and then you've got the first node's empty, so then you can kind of use that one.
yeah,
Um, Otherwise, you gotta do like copying within nodes as well, and you get even more copies.
yeah.
Um,
Because we
um,
could literally do like this. We've got one, two, three nodes, and then we call compact, and we'll see, okay, the first node has got a bit of space. So the compact will actually fill up the first node, so it's 100% full. Then
yep,
drop the
and we'll
second
fill up all
node
the nodes to be
if it
100% full,
yeah, and just
and
literally do
then
copies. Yeah.
yep. And we do the same thing for insertion, or what? Like insertion, we can just keep the same code that splits a node, but um,
Yeah,
yeah, then we just need compact afterwards, perhaps. I don't know.
exactly.
Basically,
Yeah.
when
So
we
we,
modify, we always insert and remove at the same time. So we can like remove first, then insert, and if we get lucky, we can reinsert in roughly the same place, and then we can compact.
yeah, yeah.
Um,
And it's actually very simple to split it like that because we don't have to worry about the cleanup stuff or it's actually maybe a bit safer. The
cool.
code is just very simple, fast, easy.
Yeah,
I don't
that
know how
sounds
you
good.
feel. Yeah. I'm
Yeah,
happy if you
I'm
if you
finding this more and
want.
more attractive.
Okay, cool. We can still, if you like, we can finish up this merging that we're doing. Uh, but I
Yeah, I mean,
really
if we're gonna
like
throw
the
out this code,
sim
maybe it's not worth it. I don't know.
exactly. Yeah. And unless later we want to use this for other applications, but I don't think we should worry about
Yeah,
that now.
maybe it's
Yeah.
not. Yeah, I don't know, but it's also like only like a few more. I mean, what do you need? What do we have left to do here? I guess there's some tricky logic here. It would take us a good half hour to do this, I think,
Yeah.
um,
Yeah.
to do it properly.
Yeah.
So maybe we can just say, yeah, panic or
Yeah.
I want to just put a compiler here,
Okay. So you're happy,
just to make sure
Isaac?
we
You
don't
think
actually use this.
yeah. Are you thinking like you're getting excited, like just very simple batch?
Yeah, I think your just rebuild the whole thing idea is better. It's
Okay.
simpler and it'll give us a more optimal tree for iteration, which is what we need for query speed.
Yeah.
Um,
Yeah.
cool.
Which makes me wonder actually, like we do have to have a segmented array for static allocation. Otherwise, we could just have a fixed array. So that's actually the
Right.
reason why we're using the segmented array. But we don't really worry about insert speed. We're prepared to skew stuff a bit, like we're biasing in favor of the common case.
Yeah. And
Nice.
it actually does make batch inserts a bit nicer if we don't have them like all at once. Like doing a series of like single element inserts and then rebalancing is better here than with a fixed array.
Yeah.
Um, because we only have to like copy the elements of one node instead of shifting for every element in the array for every insert.
Yeah.
Um,
Yeah. Exactly. That is better too. Okay. I've got to head off quickly, so
all
we'll
right,
be back
cool,
on. Yeah, shall we be back on in an hour and a half? It'll be half
cool.
past 10, sorry, half past 11 your time, or half past 10
Yep,
UTC in an hour and a half.
yep,
Cool. Yeah,
cool.
catch
I'll see
everybody
you then.
later. Yeah, yeah, awesome. Have a nice break. Cool.
You too.